Hello, and welcome back to the video lecture series for Introduction to the Art of Programming Using Scala. In this video, we continue talking about methods that exist on the sequence types. In particular, we are focusing on array and list. And we've looked at a number of different methods. We've talked about the kind of basic methods that you can call on them. We've also talked about higher order methods. In the last video, we looked at how we could put some of those things together along with recursive function to load in data and then to find out things. In this case, we were looking at weather data and to pull out information. In this video, we're going to look at a set of methods that give back things called iterators. And we'll start off by working in the REPL. And we'll go ahead and we'll make a list. Make a variable, call it LST, and it will be a list. And I'll just make a list of integers. Some random numbers. And so with that defined, we know that we can do a number of different operations on this. The first new method that we want to look at is called tails. Now, you should recall that on a list, if you call just tail, it gives you the list of everything except for the first element. So what happens when you call tails? Well, now this is interesting. It gives us back an iterator over a list of int, and it prints out just saying non-empty iterator. And so this begs the question, what is this thing called an iterator? We will see the iterators again when we look at files. The idea of an iterator is it's much like a sequence where you have one element followed by another, with the difference that in iterators, as you get each one, it is consumed. So in a fundamental sense, the iterator has two main methods. So if we make a variable name for the tails instead of calling it iterators, how about I call it tails? There is a method that tells us whether or not there is another element in there, and then there is a method that gives you the next element. Okay. Now, what do we see here? When we call this, we got back, well, the whole list on it. And we can ask, does it have a next? Yes, it still does. And we call this again. And now we get a different list event. It is that list, but one shorter. There's still more, though. You get this. And then there's more. And you get this. And actually, I can run through these quickly by doing tails dot for each print line. Remember, for each is one of those higher order methods. It just runs through everything and applies a certain function to it. And you can see that the remaining tails are, everything gets shorter and shorter until we get to an empty list. Now's where things get a bit interesting, though. What happens if we print tails now? Now it is an empty iterator. Unlike a list or an array, where all of the elements are stored somewhere in memory, the thing about an iterator is that you really only have to have one element at a time. And we'll see some of these methods that can give us iterators potentially have a very large number of elements in them. And so for memory reasons, you don't want to have all of them. You only want to have potentially one at a time, or only keep track of the ones that matter to you. When you are done reading this iterator, it's now empty. Okay? There is nothing else left in tails. And I would have to call the tails method again to get a new iterator that goes through these. Just like tails runs through and gives you successively shorter lists where you drop off items from the beginning, there is also an inits method, And if we immediately pipe that or send that into a for each and then print line it, you can see that what inits does is it also gives you consistently shorter and shorter lists, but it pulls off elements from the back instead of from the front. So if we compare that to tails, you can see the difference here. Yeah. Once again, both of these are iterators, so it didn't actually have to create, especially in the case of tails here, it didn't actually have to create all of these different lists. In the case of inits, it winds up, it did create all of these lists, but not all at the same time. Once it was done with this one, it could go to this one, and when it went here, it could throw away the previous one, etc., etc. So, being an iterator, each of these elements is consumed, and unless we keep track of it in some other way, it is not going to stick around and be useful to us. Now, why would you want to have these types of methods? Inits and tails, maybe you can find some reason why you wanted to look at every subset. Actually, I can think of certain things in where I've done data analysis and you want to do some type of a cumulative sum. That would actually be the inits. I might actually reverse this, so you start off with nothing, and then you have the first data point, and then you have the first 2, and the first 3, and the first 4, and the first 5, etc. And so you would run each of these through some processing to get values out from them. It's worth pointing out that iterators can be converted to lists or to arrays, and so we can get a list. Now, of course, this causes all of them to actually be in existence at the same time, and that can be inefficient for some of these methods. It's probably not horrible for inits and tails, but we'll see some very shortly where the number of elements is very large. Another one of these methods that gives us back an iterator is grouped. And so if you just call grouped on that list, once again, we get a non-empty iterator. We can see, for each print line. We can see each of the elements by passing them through print line. And now to see what that was doing, let's compare this to our original list. So the first 3 elements are here. The next 3 elements, the 5, the 8, and the 4, are here, and everything that's left comes there. What if we had done a grouped by 4? Well, then we get the first 4 and the second 4. If we had done a grouped by 2, we get these in groups of 2. Okay, so what grouping does, this method gives you back an iterator that runs through groups of whatever size you wanted. Go back to the weather data that we had. This would be a fast way of getting data that is organized by weeks. So if you did grouped by 7, every grouping would be a list of data that represents 1 week in there. And so then you could do something like take the weekly average for high temperatures and do something with it. So grouped would give you the ability to pull off that data and utilize it in a helpful way. Another thing which has a similar type of usage is, instead of grouped, it's called sliding. Now, so it gives us an iterator. If we print all of these out, what sliding does is it's kind of like grouped, except that each one, whereas with grouped, everything that went into the first list winds up being kind of skipped over for the next one. So you did the first 3 and then you did the next 3. Here you do the first 3 and then you slide down 1 position and you take the next 3, and then you slide down 1 position again and you take the next 3, and then you slide down 1 position again and you take the next 3. So this kind of slides you through the data. A standard usage for this type of thing would be averaging over a sliding window. this works to kind of cancel out noise. So if you're in a scientific setting and you have noisy data, the noise can come from measurements or whatever, something that was intrinsic into in the system. By doing a sliding window over it, you can take averages over that, and it averages out the noise. Now you wind up having fewer data points because of this, but you can get things that are nicely smooth. Engineers wind up doing this type of filtering to cancel out noise on a regular basis. So that's what the sliding method can do for you. There are two other significant methods that give you back iterators, and these are the ones for which you don't necessarily want to have everything in memory. So let's start with permutations. And now, permutations, if you remember from math, permutations on a list of things is all the different orderings that you can have for that list. Now you'll notice here that printed quite a bit of stuff. Okay, there are lots of permutations on this. Let's make a slightly shorter list. I'll just make it so it has 4 elements. And then let's print the permutations on that. Okay. How many permutations are there on a list of 4 elements? Well, the first one was 1, 2, 3, 4. 1, 2, 4, 3, 1, 3, 2, 4, 1, 3, 4, 2, 1, 4, 2, 3. You can read through this, and basically every possible ordering of those numbers they have printed out. How many possible orderings are there? Well, the number of permutations for a list is equal to the number of elements in the list factorial. So we had 4 elements here. There are 4 factorial elements inside of this, and in fact we could call length. So yeah, 24 elements there. What about for our original list? There were 20,160 elements in that, which is why you might not want to convert something. If you call permutations on a list that is very long, and in this case very long is almost anything over 10, by the time you get to 15, as we saw when we were playing with our recursive methods in factorial, 15 factorial is a very large number. You do not actually want to create 15 factorial new lists. You will probably run out of memory on your computer. However, if you have it as an iterator, you only have to keep one of those lists at a time. Now, why would you want the permutations on something? The reason for having permutations is if you have a problem where the ordering of the elements that you're looking at matters. So, for example, maybe you're looking for some optimal solution to something, and you want to have all of the different orderings that maybe actually I'm reminded of an XKCD cartoon where they were looking for how people should be seated in a movie theater, and so each of these would represent a different person, and some people like to be by others, and so the question is, well, what's the optimal ordering? Well, one way of doing that is to run through all permutations of the ordering and calculate how good each ordering is, and then remember only the best one that you've seen. You could write your own code to generate these permutations, but Scala's done it for you, and it actually makes life very easy. If you've done, at the point where you saw permutations in math, you were doing something related to combinatorics, even if that term wasn't necessarily used. There is a similar function. Instead of doing a permute, you can do a choose. And so remember, LST has what, 9 elements in it? Oh, 8 elements. Okay, so LST has 8 elements in it. Standard problem that is given out occasionally is you have n people in a room and everyone is supposed to shake everyone else's hands. How many times are hands shaken in this scenario? And it turns out the answer is, well, it's every pairing of two. So you have n people. How many different ways can you choose two from that? And that is exactly what combinations does. And I did it with 3. If I do it with 2, this runs through and gives us every pairing of 2 elements. Now, of course, up here it starts with a 4, 4. We did have 2 4s in our original list. That was our only duplicate in there. You can also pick every group of 3. So how many different ways can you pick 3 elements from that list? And not just how many different ways can you, what are all the ways? That's what this gives you. Now, when you do a choose operation, the combinations, it is order independent. This 219 appears here. There is not, you will notice, a 921 anywhere. That's because this is, in fact, none of these start with the number 9. This is order independent, whereas permutations was based upon order. The choice operation is not. And so, once again, why might you do this? Well, you might have a situation where you're trying to solve a problem that you want to look at different pairings or groups of 3 or 4 or 5 of different sets of data to test them to see which one is best or worst in some way. So that is that covers the different iterator methods that are available on our sequences, on our array and list. Remember, you can convert your iterator to a list or to an array. However, you probably don't want to do that, especially for the permutations and the combinations methods, because the number of elements in those can be very, very large. And because both of them grow kind of in an exponential, or not in a factorial way. Actually, factorial is bigger than exponential as far as the growth rate goes. So they can get very large very quickly. For example, on our temperature data, you would not want to consider doing permutations on the temperature data because we had over 10,000 elements in the temperature data, and 10,000 factorial is an absurdly huge number. Even if you didn't force it to build a list or whatever, you would never manage to make it all the way through all of those elements. If you tried to do something that was going to run through all of them or map them or do a for each on all of them, it would never finish because that's simply too many elements. But these can help you to solve certain problems, and they kind of give you a tool that without these methods, it is significantly harder to write code that does things like search for optimal solutions for things. So that's it for this video, and we'll come back, probably play with this and other methods later.